here with the 2023 paper two, right? In one paper two, module one we're doing, and then we'll review what we need to review from module two, then into the module two questions. How intriguing! Number one, state each of the following laws. Boyle's law. What is Boyle's law? This is crazy. How interesting. I wonder if I said that before. So what's Boyle's law, guys?
The pressure of a gas is inversely proportional to its volume at constant temperature.
Right. So the pressure of gas is what inversely proportional to the volume
Yes, sir.
at constant temp, right?
Yes, sir.
Temperature in Kelvin. All right, moving on. All right, I can't believe the first two questions is giving away free marks. Charles law. What's Charles law?
The volume of a gas is directly proportional to its temperature in Kelvin at constant pressure.
Kelvin at constant pressure. Look at that. Those are the laws, yes. All right. So the volume of a gas is directly proportional to its temperature in Kelvin at constant pressure. Moving on. State four assumptions made about gas molecules in the kinetic molecular theory with reference to ideal gases. What are four assumptions?
The gas molecules are in constant random motion.
The collisions are elastic.
Random.
The volume of the molecules are negligible when compared to the volume of the gas.
And the particles exert no attraction force on each other.
Wait, give me a second. Hold on. There, a lot of people are saying a lot of right stuff all at the same time. Size of the molecules are negligible, right? Compared, that's not what it's compared. To the volume, the gas that the gas occupies. That's not random. All right, that the gas occupies. Um,
Sir, is it size or volume?
okay, so you said the volume is negligible to the size of the. What is okay? What are two variables in that assumption?
Oh,
I just want to know what two variables are. The size of molecules are
There's
negligible.
just volume.
The volume is just negligible.
Yes, sir. The volume of the molecules are negligible compared to the volume of the gas.
Oh my gosh, the volume of molecules. My bad. All right, so the volume. All right, and then we have somebody said something else. There are a lot of assumptions, so give me a couple more that I didn't write down yet.
the collisions are perfectly is elastic.
Yeah, so the collisions themselves, right, are elastic. I guess perfect.
Sir, does that mean that no energy is lost or something like that?
Conservation of momentum, right? So the one conservation of momentum of kinetic energy. So is energy is conserved, so it's not necessarily lost. Yeah.
Okay.
And then one more.
Potential and kinetic energy of the particles are high.
Okay, the thing is no, I'm thinking about this as I write it, and ideal gas conditions are at high temperatures and low pressures. So technically, yes. All right. give us another one for good measure. Another one for good measure. So in case you
The molecules exert no force on each other.
lovely. No forces on each other. I'm so surprised that I am not misspelling more words. Okay, so let's go. I do not major in English. I currently major in chemistry and physics. So if I spell something wrong, I just saw it go and we'll live with life. A flask has a mass of whatever that is when empty, and when when 47.816 grams, right? Okay, and that was when filled, right, with acetone vapor at 100 degrees Celsius. And
Excuse me, sir. We're not seeing the question.
we're not seeing the. Are we not seeing it? What's happening?
Sorry, it just came up on screen.
My blood. I think it's just slow. Alright. It's just slow like cold condensed milk. Alright, so a flask has a mass of 392 grams when empty and 47.816 grams when filled with acetone vapor at 100 degrees Celsius and at 745 millimeters of mercury. Right? If the volume of the flask is now 247.3 mils, right? What is the molar mass of acetone given the constant to be that? Why R looks so? Given R to be that, right, at atmospheric temperature there, per mole per Kelvin, that is what R is, right? And for 760 millimeters of mercury to be equal to 1 atmosphere. What is it that we do with this question apart from skip it? What do we do?
Write the formula.
Which formula? Because the way I'm going to write, right, the formula for beer laws, beer numbers, law. I can write any formula. Which formula is it?
The ideal gas formula.
The ideal gas formula, lovely. So we're getting somewhere. So that is PV equal nRT. Why we choose PV equal nRT?
Because you have the gas constant, you have pressure, you have volume, you have mass, and everything.
Do we have the number of moles?
Yes, and you need the number of moles to find the molar mass.
Okay, alright. Is the way home look through the question? Oh, okay. Alright, so let's plug in our. What do we have? So, what is the pressure that we're using? Go ahead.
So we don't have to convert it first.
I mean, do we convert it back to original units? I would like to use SI units though, right? Technically this wouldn't be SI units technically. The formula works in a specific way, right? So are we going to convert our units back to what they were? Are we going to continue to use millimeters of mercury and stuff like that? Guys, I think you need to talk to me. And then we'll get through this.
Sir, I think that is specific convert because this is confusing.
Okay, it's confusing, so I want to make it a little better. Alright, so let's work with what's in the first part of the formula, right? Pressure. What is the pressure that we're given?
745 millimeters something.
So millimeters of mercury, right? 745 millimeters of mercury, right? So that is what we're given, Hg, right? Do we need to convert that to atmospheres? Is that what we're to do?
I guess so.
Yes.
How do we convert it to atmospheres? I would just do the simple thing like this. I'm not sure how many persons would do this.
So you were divided.
I mean, yeah, you technically just would divide it. So You'd have that, right? So you would divide what by what? 7. What would you divide by what?
You divide the 745 by the 760.
By 760. Sorry, that would get 766. And that would give us
0.98.
okay, 0.98. Let me just make sure that it's 0.98 for through. Alright, 0.98026. Alright, so 0.980 is what I'm going to use. So I have 0.98, right? Okay, sure. 0.98 watts. Atmospheres, right? ATM. Atmospheres. Lovely. So we have pressure. What's our volume now? We have one variable now. What's our volume?
247.3 milliliters.
Do we have to convert that to some? What is the volume that we use? Like, do we have to change it? Do you think so?
So we would have to convert it to liters.
Who
Sir,
agrees? Go ahead. Sanjay, you're saying? Sanjay.
Yeah, I don't think we gotta convert it to liters because I think and nothing else in the formulas are dealing with liters.
Okay, you're saying that nothing else will be affected by the volume. That's what you're saying. So it should be
Yeah.
fine. That's what you're saying. Okay.
so but
That's
look at
irrational.
the units for R.
For R, atmospheres per mole per Kelvin. Per mole Kelvin. The units of R, atmospheres per mole Kelvin. Okay, so looking at the units of R. Wait, am I looking at it wrong? What is that? Is that a L?
Is liters
Is
for
that
atmosphere.
Yes, sir, that's
is that
liters.
L? Oh my! I would have never. Let me. Okay, give me a moment. Let me go for my glasses.
So we would convert it to liters.
Yeah.
Well, yeah, that makes sense now.
Why? Now I can see. Alright, so liters. So no, Shonji, do you think that we should convert it to liters now?
Yeah.
Yes, sir.
Lovely. So what is the answer now for this conversion? What do we do to it? Do we times it by 3? Do we divide it by pi? What do we do?
Divide it by 1,000.
So you're saying that we divide it by 1,000, everybody should be in agreement. So we divide by 1,000, what do we get?
0.247.
0.273.
Okay, 0.2473. The thing with me, I tend to keep as much decimal places as acceptable before I start rounding up anything. Right? So to get the most accurate value, because when you start rounding early, your answer starts to vary from what we want it to be. Alright, so that is what we have so far. Volume, pressure, down. Do we have the number of moles N?
No, but we have the mass.
We have the mass. And what is the mass that we have?
You have to subtract 447.816 grams from 47.396 grams.
I'm trying to write on this page, and the page not giving me justice. 392 grams.
So wouldn't you have to convert it to kilograms?
Okay, I think the difference. Okay, hold on. I'm gonna ask you guys a question, right? So if I convert these to kilograms and then minus them, or minus them then convert them to kilograms, should I get the same answer?
Yes, sir.
Yeah.
Yes, I would. All right. So I would minus them. I would just stop. I would stop myself from trying to convert two things and then doing that. I just minus it and then convert once, right? So 47.816 minus the 47.396 0.392.
You get 0.424.
0.424. And what would you know? Convert it now. This would be grams. So convert it to kilograms. What would that be now? Times it by a what? 1,000?
Divided by 1,000.
Divide it by 1,000. Alright. So we have 0.424 divided by 1,000. Everybody agrees?
You get 4.24 times 10 to the negative 4.
Times 10 to the negative 4 what? Kilograms.
Kilograms. Sir,
Lovely.
but like in this case, I don't understand why you're changing it to kilograms.
Okay, why? Okay, what's happening?
Because now like I know when you look at our constant and you look at everything, I know that this not gonna affect anything.
Okay, but hold on. We're using the mass to find the number of moles of acetone, right? Acetone. Is that what we're doing, right?
Yep.
Hold on, that's so weird because unit 1 students don't technically touch stuff like that. But okay. Acetone vapor. Alright, sure. Publicity, interesting. Alright, so what's gonna happen here now? In order to find the number of moles of a substance, do we use it in kilograms? Do you use kilograms to find the answer?
Sir, wouldn't you use it in grams?
Use it in grams.
Grams, sir.
Alright. So convert it to kilograms. Why? Probably because I want to show. Go ahead. Okay.
Sir, sir, we'll leave it in grams, right? Because we're trying to find molar mass, which is in gram per mole. So we don't need to convert it to kilograms.
Exactly. Alright, so I want us to see stuff though. Because when I do passive pause, I don't just bring the question and I just do everything in front of you and then move on. No. We work our way through it. Alright, so we convert it to kilograms. That's what we have on the paper that we do. Alright, so first of all now, how are we going to use the mass, right? And the rest of the information. Okay, we have 100 degrees Celsius there, right? Convert 100 degrees Celsius to Kelvin. What do we do to convert it to Kelvin?
You
We
add
just
200
add
and
273.
0.15. 273.15 should give you it in Kelvin. What is the answer?
So we have to remember the 0.15 part.
I guess it's a thing that I always do. I always have 0.15. It's more accurate.
Okay, sir.
Sir, I don't think you need to remember that.
Yeah.
Okay, you see the thing about me, right? I have been traumatized at the university level for living off the 1.5. So.
Yeah, sir.
Sir, them too extra.
Sir, is it 1.5 or 1 point? Is it 1.5.15 or 1.16?
What? Wait, hold on. I'm so am I writing something that doesn't make sense?
No, sir. As in, is it 273.15 or 273.16?
Leave it as 1.5. Right. I'm gonna use the 1.5, right? But if you want to leave off the 1.5 or don't remember it, then it should be fine. Alright, so that's what I have for the temperature in Kelvin. Right, so we have everything and we have our gas constant now. Now, what we're going to try to find is small n, right? Is that what we're going to try to find? And then we'll try to find small n now, the molar mass. Guys, are you guys following me?
Yeah.
So, how do we calculate molar mass in the first place?
Moles divided by mass.
Moles divided by mass?
Molar is mass over molar mass to find the moles.
Alright. Zach, you want to say something? Raise your hand.
Sir, she already answered the question.
Alright. So, reiterate. Molar mass is equal to. So, molar mass is equal to what? Just repeat.
Given mass over molar mass.
Given mass over the molar mass. Hold on, that doesn't make any sense.
Wait, sir, what you asked, sir?
How you find molar mass?
Sir, isn't it moles divided by mass?
Oh, sir, moles. Number
Oh.
of moles
Divided by mass, right?
times.
Oh, channel. Okay. Hold on. No. I'm confused, right? Because we're saying that it's moles divided by the mass, right? And some people are saying the mass divided by the moles or the moles divided by the mass, all sorts of something. How do you calculate this?
Sir,
Mm-hmm.
moles equals mass over molar mass.
Mm-hmm.
So if you transpose,
Yes.
you carry over molar mass. Mass going equal to mole times molar mass, right?
Yes.
And then you carry it back over. So mass over mole not going equal to molar mass.
Beautiful. Mole, right? So that's what we needed, right? So what we need to get from PV equal nRT is the N. So we transpose now, what are we going to get? N is equal to what? PV over RT, right?
N is, yeah.
PV over RT. And when we calculate that, what we get? PV over RT, just write in the whole of our all equation, plug in everything. What's N? Zero 0.980 times our volume. Yeah, I'm so sorry about that. Let me put the L here. It's liters. And then we're going to divide by R. Use the R value now because we know that R is 8.314, but they told us that R in this case is different because R changes depending on the pressure, right? R is for atmospheric pressure. So this R changed, which is a constant. And then we times it by the temperature. What's the answer, guys? What's the answer? How many moles? Hello?
Sir, where's the calculator?
Sir, 0.079.
Okay, that's an interesting value.
I got 7.91 times 10 to the negative 3.
That's also what I
Also
know.
got that.
Okay, so the person who just spoke 0 point something, the answer is right, but the decimals are off. Check what your calculator.
Yeah.
Like, check your calculations. For my calculator, I can just write in the vernacular and write the entire equation one time, right? So,
Yeah.
just do all of that.
Sir, 0.0079.
Could anybody explain why you keep on getting
Yeah.
0.00?
Sir,
Uh-huh.
yeah, value is 7.9 times 10 to the negative 3.
Yes.
So if he value is, where's your value? 0.0079
Oh, it's just flat without the time to
is, yeah, we get it in exponential and he get it out standard. So his value is correct.
Okay, so his value is correct. Alright, lovely. So 1.91, and then we get the times 10 to the negative third power. Right. So what we need to do now is get our mass in grams, because that's how chemistry works. Right. So 0.2. Wait. 4.24. Right. So 4.24. Right, times 10 to the negative 4. And we're gonna divide that now by the 7.91 rather, times 10 to the negative 3. Is that what we do?
Sir, no, it's supposed to multiply. Are we finding the molar mass? We're finding the molar mass, right?
The molar mass.
Yeah, we're
Sir,
finding the
if you're
molar.
finding the molar mass, shouldn't you use the grams value?
Wait, no, never mind.
Yeah, yeah, it's the gram. Oh my gosh, I just messed up everything.
No, it's not gram. Yeah.
The gram value I should be using, because I know it's the gram values, but I just looked at the wrong number. Okay, let me remove that because we did say that we're using the grams and not kilograms. Alright, let me remove that in case anybody takes that value and puts it there. Just like I did. Go ahead, somebody's saying something.
So, sir, why did you convert to kilograms, sir?
Okay, so how I do past records, right? I walk through with you guys to see what you guys do, and then I correct if we're going directly off the tracks, right? So somebody said to convert to kilograms, so I convert to kilograms, right? And then we started to ask the question whether or not we need the kilograms, so why we convert in the first place. So that's why, right? So we were converting to kilograms, and then we realized now that okay, we do not need kilograms. Right, so it's just something how we're able to realize the question and do stuff and figure out what we need and what we don't need to do. That's the only reason why it was calculated in the first place.
Sir, so the molar mass is, well, I got 53.58.
0.58. Interesting. This is acetone.
That's not what I got.
I got 53.6.
Same.
Well,
53.58
Yes,
and
that's
6
wrong.
same thing.
3.6.
Same thing.
Wait, yes, it's the same thing. It's the same thing.
Yeah.
So my answer is 53.6 flat and not 58. People be rounding places, and I be rounding as well. So it's 53.6 basically. 53.58, 53.6, same answer. Well, obviously mathematically it's not the same, but chemically it's enough. So the
Yeah, I have
answer.
the same answer.
Oh, the same answer. Alright, okay, so 53.6 what? Bananas. Cars, papers,
Grams per mole. Grams per mole.
grams per mole. And that's that. So this is a question in which they get you to use your kinetic theory and your moles at the same time. Alright, so that's the answer that we got for this. Any objections, any issues? So where I ask now for the persons who are looking at things and saying, how you get that? What are the questions? Alright, seems like everybody's fine. Or sleeping. Alright, so we know we stated this already. What's Hess law? State Hess law, please.
Hess law states that the enthalpy change of a reaction is independent of the route taken by the reaction.
Give me a second, let me just type everything and then fix all errors of the. This is a simple one. Go ahead. Somebody raise them hand up. Shall they go ahead?
First, sorry, completely off topic. I was just wondering, if we'll be doing the next modules another day.
I don't think you.
We won't do that.
Okay, we're gonna go until the Lord says stop. I mean, when is your exam? Not Tuesday?
Yes, sir.
So anything, I'm going to be going through, until, as I said, the Lord says stop, right? Which is probably after 9, after 10. I don't know when we're going to stop, but I'm gonna record as we do the papers, right? Anything that's left off, there is this wonderful day that the Lord will hopefully make, which is Monday, which is the day before your exam. We'll try to complete the other modules. Anything that's left off. Module 2 is a bunch of calculations, so I doubt there's a lot of information you guys want to review. We'll just get into past papers, I guess. For that. But let's look at this. Construct a Born hypercycle for the formation of lead fluoride. How boring. Showing clearly, using equations, the steps of enthalpy changes involved. Alright. So from formation of lead, that solid showing. So what are we gonna do here? I'm gonna just draw a long line down here. All right, and down here is what our lead is, lead 2, right? No, it's not. It can't be lead 2. Oh my gosh. All right, it's gonna be lead difluoride. So we're gonna have PbF2. Okay, so how would this diagram look? We're starting over
So you
here,
would
right?
start with the enthalpy of formation. Yes, sir.
Yes, enthalpy of formation. And then what we get up here now? What would be up here now?
We're gonna get lead solid and half of fluorine
Because half of fluorine.
in gas form.
Yeah, okay, so half of fluorine. Alright. What we're going to get now.
Above that,
Wait, sir, I am not understanding. Why do we need half of fluorine in this case when we already have 2 fluorine in the formula?
oh,
Because it's
makes
supposed to be
sense.
1 mole.
Will just be F2, sir.
It would be F2 for real.
Yeah, the F2 comes to say.
Oh
Yeah.
it would be F2 for real.
If it was just lead fluorine like PbF, then I would understand why you have half, but we don't have that.
Okay, you know.
Yeah, it was a mistake.
You know I will have a. Oh, okay, you know as well we'll have half. We're gonna have 2 ionization energies. Alright. So I don't know if we can. Oh my gosh, writing on a screen is so weird. If I had a whiteboard and I was in front of everybody, then everything would be better. Alright, hold on. Alright, so let's do this part now. So we're going. What is this now? What we're moving? What we do next? We're ionize. We're atomize rather, right? Hello.
Now you're gonna get entropy of atomization of lead, and you can get lead gas plus F2 gas.
All right. Next step. What's the next step?
The first ionization energy of lead.
All right. So we're gonna ionization energy, and then we'll put a little 1. First ionization energy of lead. That should give us Pb plus G, right? Plus E plus F2 G. Alright, that makes sense so far. Next step.
Sir, after this, I think you would have a second ionization energy of lead. I'm not sure.
Yes, you would. Ionization energy of lead. Right, we're gonna have Pb 2 plus now, right? Plus 2 electrons. Forgot to put the charge on my electron. Electrons don't have states, guys. I see people put electrons in water. I'm like, okay, interesting. Electrons are not things like that, so you can't. Oh, I forgot to put my gaseous ion there, because that's what ionization does. I'm so sorry. This is going to look so weird, but we're trying our best. What's gonna happen next?
Affinity of fluorine.
The bond. Oh no. We have a bond dissociation, no? The bond dissociation, yes. Yeah, we're gonna have bond dissociation of fluorine. Because what we're gonna end up with now is this long line up here, where we have Pb 2 plus gaseous form, yeah, and we're gonna have 2 electrons, yeah, and we're gonna have 2. Hold on, this is weird. Oh yeah, we're gonna have this 2Fg, yeah, and then now we're going to go down. I shouldn't put the arrow there. I should put the arrow on the other side. No, the arrow doesn't matter on which side. No, I just want it to look better. Alright. So we're gonna have that, right? And we're gonna go down now. What we're gonna have here now, the first electron affinity now of the fluorine. Right, but the thing is now the first electron affinity of the fluorine that will encompass everything in one step. Right, so let's look at this. Pb2 plus gaseous, right, plus 2F minus gases. Right? Because why I think it should be done like this is because I don't understand why you're going to have one fluoride ion and then another electron and do it again. That doesn't make sense. Because the energy you're applying to the system is the electron affinity of fluorine. So if you have all 5 fluorine atom, right, then you should still be adding the electrons for all 5 of them. So I think it's just going to be one general electron affinity because you have 2 electrons and 2 fluorine, so you're gonna end up with 2 fluoride. I think that's how you do it. If you want to combat it, you can combat it. What would you guys do? You'd put 2 separate steps?
Yes, sir.
But what would the second step be? The second electron.
Sir, wouldn't it just be one step? Because remember that the fluorine just losing 1 electron, and that will go for both the
Gaining.
moles.
Alright. So gaining 1 electron, and that will go for both the moles. Because the thing is that if you put a second step, you will be forced to put the second electron affinity, and that will give us F2 minus. So I think it should be 1 step. Right? That's my reason. I think it should be 1 step. Right? And then after that now, we're gonna end up with something interesting. Do we draw the arrow straight back down to the first line?
Yes, sir.
Yes, sir.
And what do we call this now?
Sir, the lattice.
So let me put the electron affinity here, and then this would be our lattice energy. Why am I drawing a T? Hopefully that removes.
Sir,
Go ahead.
something about this thing look very weird.
It's
This thing in the plate. Because you get lead 2 plus, and you get 2 F minus. This
It feels
like
weird
you
because it
remember
doesn't look
when
like the
we
others.
make it. Pardon?
It doesn't look like the others. But okay, go ahead, continue. I don't want to stop you. Go ahead.
Remember when we get 2 atoms come together, right? We get Pb2 plus and F minus. And you just swap the charges, and there you get PbF2, right?
Oh, that's how you write out ionic formula, yeah?
Yes, so in this case, you get Pb2 plus 2 F minus. Like, what are you doing with this extra F minus?
Okay, it's because... Okay, let's look at it. Alright. So, why we have that other F here, let's look at it like this. At the end of the day, you know, the molecule is generally this. At the end of the day, it's that, right? Because you know, you switch molecules, the charges aren't right, your ionic formula. I know, yeah, you are completely right. But we need 2 fluorines because we're gonna need to cancel out that negative charge there. We need to conserve the mass. Because if we just move from 1 fluorine and then our formula just becomes PbF2, we have to show that there are actually 2 fluorines existing within our entire cycle, right? So it's something like that. We have to show that. So it's not that we have an extra F, we're accommodating for the 2 F's that must be present within our formula. Which is our lead fluoride, or lead difluoride there. So it's not extra F's per se, but it's accounting for that other F here, present here, that is written on the molecule. Because it shows that there are 2 F's, so we must accommodate for that. Tech age, this is a lot to say. Alright, hopefully that makes sense. Is that the end of module 1? Oh my gosh. I'm so sorry, this is so much work. So okay, you could actually look at the paper to see if you had everything. See it there, we had everything, and there's not 2 electron affinity steps. So see it there, we have everything. Alright. Atomization, yes, we have everything. Do we have everything? Let me check something real quick. We have the atomization of fluorine and the atomization of iodine. Not iodine, lead. Where are the writings?
No, sir.
Oh, we only have 1 electron affinity. Okay. You see what's happening here now? You see, this is the problem now, right? You see that electron affinity for fluorine that you're talking about? That's gonna be same to that is the bond dissociation, right? Because the concept, the theory states that the atomization of a diatomic molecule is called the bond dissociation energy, right? So if you learned it like that, which is in actuality, right, you're just going to put the atomization of fluorine, right, to be where your bond dissociation of fluorine is. Hopefully that makes sense. That's what we're gonna do. Because it's gonna be the same thing. Because what bond dissociation is the atomization of a diatomic molecule. That's all it is. Hopefully we got that information, right? Using the table now, calculate the lattice energy of lead fluoride. Alright, so what is it that we do now? Hello?
You would have enthalpy of formation, and you would subtract everything else from that, right?
So you have formation and you subtract everything else from that. That is what I'm hearing. Alright. Any other things that you guys may put forward?
Excuse me, sir. Is the formula formation subtract the sum of the intermediate processes?
Alright, hold on. Let's look at the table. Alright, so let's go in the direction of our reaction generally. Alright, let's wait for the table to load that we just drew, which should more or less be the fine table. Alright. So right, what we're looking at, right, Hess's law that says that it's a sum, right, of all these intermediates that we're gonna use in order to get our overall reaction or lattice energy. Alright. So what is it that we do here now? So what I would do in this case, right, I would try to add everything, right, and then what I would do is minus that heat of formation there, right? And if you're minus a negative number, what you're doing is adding the heat of formation. So it's the same thing as just having the heat of formation and then kind of like just taking away everything else in a sense. So if we look at it like this, right, we have these jumps. Let's use different arrows, let's use different colors, right? So I want you to stop me if it's not making sense, because if it's not making sense, it don't make no sense to continue. So stop me if it's not making sense, right? So we're jumping, we're having this. What we're going to do is add these. We're adding that, we're adding this, we're adding this, right? We're adding that, right? And I think at the end of the day here as well, we may add this, right? And then what we're going to do is technically we're just going to be minusing this down here, right? So this is going to be another one. We're just gonna minus this down here, which is minusing a negative number, which is generally just adding it, right? So that is what I would do, right? some of them is adding negative numbers, right, and stuff like that. So some of them are negative numbers, etc., etc., etc. What we want our lattice energy to be, right, is something, I think, exothermic, right? So if it's going to be exothermic, what's the charge? What's the sign that we must have on the answer? Should be negative, right?
Negative.
All right. So if we do it if you do it in the way that you propose, right, and it is positive, your answer is wrong. So it should be negative. So question now: how many persons would do it like this? I don't know if I write it out, it make more sense. Does it make
Yes,
sense?
sir. Please write it out. I am very lost.
Okay. Let's have a look at that. I notice that people just have different ways of doing the same thing. Right. So electron affinity. This is not in order. Is this in order? This is not. This is annoying. This is not in order. Is it? In terms of atomization of that thing, it is in order because this would just be the bond dissociation. All right. So what we're gonna do? We're gonna get. Let me change this back to something that makes sense. Let's get black, I guess. Right, 195.2 1. That would be 7. 1 6. That looks weird. And should have a point. This writing thing is not fun. So 7.16, right, plus 1,450, right, plus 79, plus, wait, that would be the formation. This is the first selection affinity of fluorine. Alright, so we have that there first, right? So these values now, let's go back up. These values now.
Sir, the first ionization is 716.
716?
Oh boy, my brain. Yeah.
Do I not have? Oh, that's 7.716. My bad. Alright, so we have that there, right? So what's going to happen here now? So we have all of those being added up. Those are all going in the same direction, right? Now, what you guys are saying is that because these are formation and the electron affinity are going the opposite direction, right? We're doing the opposite operation to them. We're saying we're gonna minus them instead. Is that what we're saying? The persons who get this topic, I'm asking.
Excuse me, sir.
Uh-huh.
So when we're going up, we add, and when we're going down, we subtract.
Right? That is what I'm proposing, yes.
Okay.
Alright, so what's happening here now? Does anybody have any objections to that though? I'm not hearing anybody, you know.
Sir, how about like we work it the ways that we know and we can compare answers when we finish?
Okay, we can work it the way that we. Okay, just try that then. Because I don't want to do anything different to what you understand and then mess that up. Shouldn't be doing that. Alright.
Sir, for the first affinity energy, would you times it by 2?
First affinity. The first affinity energy? When by the first
Yes, sir. Wouldn't you multiply it by 2?
You would have to times it by 2, yes. You have to times it by 2 because
Okay, thank you.
I'm going to propose. Okay, so I'm going to do it in the way that I do it. I want you guys to do it in the way that you guys do it, and we'll see what the answers we get are, and then we come to discuss what answer. Well, if our ways are the same thing but a different flavor of calculation. Alright, so I will do now the enthalpy of formation equal enthalpy of formation negative 664. This is going to be alright. So everything stops. This is anybody getting any results yet? So what are the answers that you guys are getting for this? In kilojoules per mole, by the way. I mean, everything is in kilojoules per mole. Just remember to write your kg per mole. Waiting on you guys' answers. I'm going to do my method twice to make sure it makes sense. What are the answers we're getting? Alright, I think we're taking a bit too long. Go ahead.
2,800.
2,800 and what?
2,855.04 kilojoule per mole.
Is it positive or negative?
It will be negative because it's lattice energy.
Because it's what? Because it's what?
Never mind, sir.
Okay, so it will be negative because of it. Somebody raise their hand, go ahead.
Sir, 1,290.04.
Is it negative?
Sir, I get 3,760.52.
Interesting values, but is it negative?
No, it's not negative.
But the thing is that the theory states that the lattice energy value will be negative.
This is why.
Sir, aren't we just calculating the sum of all the intermediates right now?
Okay, alright. Technically, yes. Technically. Right. But let's have a look at this, right? Not necessarily. So I have a method. I'm not sure if my method is the fine method, and I don't want to stop you guys from using a method that you understand. Right? But I'm going to go anyways and do my method and show you guys what I would do in this case. Alright? So here's my method. Right? Because honestly, I stopped using this to calculate this long time. We don't do this anymore. So this is my method specifically, right?
Sir,
Go ahead.
what you say is the lattice enthalpy? The lattice, yeah, what is the lattice enthalpy?
Lattice enthalpy?
Yeah, because I know the lattice energy is the amount of energy required to turn an ionic substance, 1 mole of ionic substance, into its gaseous state. So I can hear you say it has to be negative. I didn't know that.
Okay, you're saying lattice energy. Okay, we're talking about lattice energy. Okay, so lattice enthalpy and lattice energy are two different things. I didn't know we made that. Okay, we made that. Okay, we're gonna make that distinction, right? There are two separate things generally, right? So looking at it from the Born-Haber cycle, though, right? This is what I would generally do in order to find the lattice energy. I'm just gonna propose what I would do, right? So the thing is, no, the enthalpy of formation, right? For me, the enthalpy of formation per se, right, would actually be equal to everything here, right? To the sum of everything here. Because the enthalpy of formation is the amount of energy required to form the substance itself, right, from its regular ionic state, well, not ionic state, from its regular states, right? So it's the amount of energy required for the entire reaction to occur by the definition of what the enthalpy of formation is. So the enthalpy of formation, right, would be equal to the enthalpy of atomization, right, of the lead, right, plus the enthalpy of ionization, the ionization enthalpy really, 1 of lead plus ionization enthalpy 2 of lead, right? I mean, this is basically what we're doing, right? Plus the atomization of the fluorine, right? So the atomization of the fluorine, which is basically the bond dissociation of fluorine, same thing, atomization of fluorine, right? Plus the first electron affinity, right? The electron affinity. This is how I would do it. The electron affinity of the fluorine, right? Plus the lattice energy. That is what I have. That is what I would do, right? So what I would do now, right, is sub in all my values, right? I would just, why is this doing that? Okay, I would sub in all my values. So after I sub in my formation, everything, right, I would actually just sum all of these, right? And we know that with times the first an electron affinity of fluorine by 2, and we know that those are negative values, so we keep them negative, of course, right? Where I would sum all of these, right? And after I get that, let's call that sum, right? Just for arbitrary sake, let's call that sum x, right? So x would be equal to the not the electron affinity, the heat of formation, which is negative 664.0, right? 0.00, plus the lattice energy. Therefore, the lattice energy is going to be equal to negative 664, right? And that would be what? Minus x. And if I do that, you are going to get a negative value, right? So that is how I approach the question, right? Based off of the definition of formation, and that formation will be equal to the sum of all steps. And if lattice energy is a step, then just sum everything, right? And then find lattice energy from the entire equation. That is what I would do. When I do that now, I get negative 2,447.68 kilojoules per mole. That is what I did. Right, I'm not sure if anybody else got that value. Did anybody else get that value? Okay, I heard a raise hand. Go ahead. 2 persons. Divine and Zach. Both 2 persons raise their hand. Go ahead.
Basically, what you're saying is that you would just add up everything except the formation, the enthalpy of formation. You would add up everything, and then you subtract that from whatever the enthalpy of formation is to get the lattice energy, right?
Generally, yeah. That's your thing? That's what you did?
Sir, I'm just following what you said that you would do because this is honestly confusing me. So I understand what you're saying, so I would just use that way.
Okay. Alright, so this is what I would do, right? So as I said, based on the laws, well, the Hess's law, right? Well, let's start from just what the formation is. The enthalpy of formation, right, is the energy required for this entire reaction to occur. And by Hess's law, right, if this is the end, this is a change. Go ahead.
What is it again?
Hold on, that's a lot of echoing. Go ahead, let me echo itself. Go ahead.
What was the value you got again?
Negative 2,447.68. Whether the value is...
Oh, sorry. I got negative 2,385.6 square.
That's not interesting. Okay, so what I'm
Sir,
saying
will you
is
say you got there?
the value I got is on the screen. I'm gonna just write it on the bottom. That is the value that I got.
No, like what you said is your formula.
Okay, I'm going to go through what I'm talking about because I think I'm confusing people, right? So what we're saying is that the enthalpy of formation is the energy required for the formation of this compound, right? That makes sense, right? And what the Bohr-Haber cycle is doing is looking at each intermediate step for this to occur. Because that's what the Barnaba cycle is, right? So instead of us just writing lead plus fluorine gas gives you lead fluoride, right? We're actually
Sir,
showing each individual step to get to the lead fluoride. Go ahead.
sir, I asking like with your formula, like your formula would be lattice entropy equals entropy of formation minus the entropy of everything.
Yes.
This the formula that the study guide gave.
That's the formula that study guys give? Study guide
Yeah,
give?
I'm looking at it right. Yeah, it
Interesting.
makes sense now that I'm seeing it. Yeah, it makes sense. And the thing with the entropy of formation, that would be positive. They would change the sign for the like, cause it's saying this is with sodium bromide, and it's saying the entropy of formation is negative 361. But when they're applying their formula, they change it from negative 361 to positive 361. And
Oh,
then
guys,
you
because we're going
subtract the
backwards.
pardon?
So, oh, because we're going okay, we're going in the opposite direction of the enthalpy of formation, so that would become a positive value, and I actually forgot to implement that. Alright, but give me one moment, let me fix that part, right? I'm trying to explain why that is, right? So let me just complete this and then we'll get back to that, alright? So what I'm saying is that the enthalpy of formation is all of this combined. Because what Hess's law is stating is that each of these individual steps that we're looking at, I'm not sure if you guys can see like the pencil on the screen, but each of these individual steps that we're looking at, the atomization, the ionization energy, all of these different things are all equal to the enthalpy of formation. Because all of that, right, is through Hess's law. So that's what I'm saying is that if all of these are equal to the enthalpy of formation and we want to find the lattice energy, right? Then add up every single thing, right? And minus that from the enthalpy of formation to get the lattice energy. So add up everything, minus it from enthalpy of formation to get the lattice energy. The lattice energy would just be one component, and that's what we're looking for. So what I have mathematically down here, right, is that the enthalpy of formation is equal to literally every step, the sum of every step, right? So I leave out the lattice energy because we actually don't have the value for that. So it's basically it's the sum of everything plus x. So find x, right? But based on the fact that we're going actually in the opposite way, the opposite direction of enthalpy formation, this should technically be positive, right? So the lattice energy should actually be this, right? It should be positive, and that should give you a different value, right? Which is if we have that positive value. Go ahead.
Sir, so I'm guessing where went wrong is that before I subtract um everything from the enthalpy of formation,
Mm-hmm.
I should have added them together instead of adding them separately and subtracting at the same time. If you understand what I'm saying.
Oh, but shouldn't that give the same? Isn't that mathematically equal? Okay, because you're saying that you add all of them separately and then. Okay, what you're saying is that you're adding, for example, you add the atomization, the electron affinity, and you add something else, and you add something else, and then you subtract instead of putting all of them in one big line and then adding them. What are you saying?
No, sir, I'm saying that
Mm-hmm.
instead of putting them in brackets like that, sir, I wrote out the enthalpy of formation minus, and then I put the other intermediates.
Okay, I get what you're saying, but the thing is not. Oh, you're just minusing it from that, right? Okay. But you should get the same answer though. Not sure what the issue is. Hopefully it's not a math issue. I'm not sure where an issue would be there from. But somebody sent in the WhatsApp group. Oh yeah, Sean J sent in the WhatsApp group that the study guide actually has the same formula that I posed, which should make sense. And that should be the answer. It should make sense. So this is the general formula, right? That's the general formula. Oh, sorry about that. Let me put the kilojoules per mole. Kilojoules per mole. So that is the general formula, and you should get the answer from that. All right. So I know it's a very
Sir,
confusing and confounding topic. Go ahead.
sir, so just when I understood, we just think the thing that I understand the formula that you showed me that is just I know that when you get entropy of formation, like to do this formula, you got to change the sign. But I turn to the other page and doing the Born-Haber cycle for magnesium oxide, and this time they didn't change the sign for entropy of formation. They left it as a negative.
Okay. So would you could send me that page as well, and we'll look at that. Have a look at that. I want to have a
It's
look at that.
literally the other page. It's page 72 in the study guide.
I don't own a study guide. So
Alright, I can send the picture.
I don't own a study guide at all. Oh, I spoke about this as well in the review earlier. This is the next part of the question here. I think this is the end of module 1 for this. No, it isn't. That's so cool. Alright. So this is a lot for module 1. But when you send the next page, then I'll look at it, alright? So state the effect of each of the following on the magnitude of the lattice energy. What's the effect of ionic charge?
As the charge increased, the lattice energy increased.
Lovely. Directly proportional, yes? So as the ionic charge increases, the lattice energy, lattice energy increases. All right, and the radius now. As the radius increases,
Lattice energy.
how does it increase though? Is directly proportional?
No, indirectly.
Indirectly increases, right? But like in what type of decrease is it? Is it an exponential increase? Like is it just a regular increase? Or you're saying it's indirectly proportional? It's gonna be decreasing, right? That's the energy gonna decrease. Okay, yeah, it's actually gonna decrease, right? But how does it decrease? Directly it decreases.
Sir, I think it's directly because if the ionic radius gets wider or larger, that means that less energy, it get less pull on the nucleus with the electrons or whatever, so is less energy needed to break them apart.
Alright. I'm trying to think of the crystal structure. Alpha is equal. Hold on, let me think about something. It will decrease. Yes, it will decrease. Yes, we know. I'm trying to figure out whether or not the proportionality is r squared, but it is not. So it's gonna decrease. Go ahead.
So I was asking if it would decrease because as the ionic radius increase, the bonds will get weaker.
Yes. Oh my gosh, this look like it spells so wrong. I don't care. Alright, so lovely. So we know what it's saying, right? This exercise is very interesting. Alright, so let's focus on that. Alright, ready. So that is it. That is it. That's what we use. Okay, so you know why though? Because this is lattice energy, and I don't think I don't know if it's in any textbooks that you guys have. But really and truly, lattice energy is this. It is equal to a constant. Lattice energy is this. It's equal to a constant, right? Times the charge of one times the charge of another divided by the distance r, the radius. That is what it is. Make sense? So if your distance increase, your lattice energy will get smaller. Make sense? So it's really and truly that. Okay? Alright, so let's have a look at this now. Go ahead.
Sir, excuse me, sir. You're saying that the radius, as the radius increases, then the magnitude of the lattice energy decreases. Is it because, like, as the radius increases, the size between the ions increases, so like there's not a lot of strong attraction forces between them, and
Yes.
so the energy, the lattice energy required to break them apart, would be lower, right?
Yes. Most definitely. Your reasoning is correct. Okay. A yellow precipitate is one. This is. Hold on. Isn't this is this module 1? This is very interesting. Alright, let's have a go at this. So yeah, a yellow precipitate is formed when silver nitrate solution, right, acidified with dilute nitric acid, is added to an aqueous solution containing iodide ions. That makes a lot of sense. Write the simplest ionic equation for the formation of the yellow precipitate. Do you guys have an idea of what's happening here? Hello?
Sir, I do not understand what's going on. Could you explain it, please?
Okay. What's going on? Alright, what reaction do we know gives us this? not know a reaction that would give us? Do we not know the reaction that's happening here? Because there's a reaction. All right. All right. So go ahead. Somebody's raising their hand. Go ahead.
So are we testing for halide?
Technically, not necessarily, but it's a test for halides. Yes, it is. It's one of them. Sure, we can say that. All right. So first of all, what we're reacting now? We're reacting a yellow precipitate with. Okay, so that yellow precipitate is formed when silver nitrate reacting with dilute sulfuric acid with something containing iodide ions. What we need is something to displace it, right? It's a displacement reaction that we're looking at. Hopefully we can see that. Can we see that?
Yes, sir.
Right? And what is a metal that we commonly know of, right? That can displace silver in this case and form a yellow precipitate.
Sir, lead?
Okay. Lead could be one, right? So it could be. No, but it wouldn't make any sense. No. What's happening here, right? Okay, we have. Okay, lead iodide. You know that lead iodide is yellow, right?
Yes, sir.
Okay, so we know that lead iodide is yellow, right? The thing is, no. We're saying that the lead iodide is formed. You're saying that yellow precipitate is formed when silver nitrate solution, right, is reacting with something else other than the iodide ions, right, with an aqueous solution containing iodide ions, right? So what we're saying is that we have an aqueous solution generally that have iodide ions in it, and we're reacting silver nitrate to the solution containing iodide ions, right? So what do you think will form? Go ahead.
Sir, since we acidified it with nitric acid and asking for the simplest ionic equation, we could get H plus I minus equals the hydrogen iodide.
Hydrogen iodide.
Will it be silver iodide?
Alright, silver iodide is yellow, so that's a little bit closer. Alright, so let's try to understand everything that's happening, right? So we'll add something yellow. Well, sorry, something yellow is formed, right? So we have silver nitrate, GNO3. Go ahead, somebody raise their hand. Dilute nitric acid, NO. Nitric, this is nitric and not nitrous. That's not going to be, it's gonna be this, right? Nitric acid, and when we react, we get something, right? So we have whatever reacting with the iodide, right? Sorry, we're adding this with some iodide ions, right? So iodine rather, we have that there, and what we're gonna get is this silver iodide, right? And then we're going to have some nitrate or something coming off, right? We're gonna have nitrates, NO3, probably as a gas somehow. Wait, is this going to be NH negative? I think so. Go ahead, somebody raise hand, right?
Sir, hold on.
So the formula here, the formula is negative, that would be it. Wouldn't this be NO3? Yeah, because NO3 negative. Alright. So we have something looking like this, right? We have some displacement. We're looking at the ionic equation, so we don't really care about the main equation. No one cares about that. What they're marking for is the ionic equation, right? So we're looking for the ions, right? The spectator ions to be removed, right? So if we're gonna be looking at this now, the nitrate itself, would the nitrate actually be dissolved, or would it come out as nitrogen gas? Not nitrogen gas, ni some nitrogenous gas, right? Some of those red fumes or brownish fumes. The thing is, now we have to understand the chemistry of the elements, we have to know how reactions work. So what we're doing now, the silver is displayed, the iodine, right? The silver is going to jump to the iodine, silver iodine is going to be made, right? And then the nitrate ions, right, will come off, right? But what is the reaction? Is there going to be the release of some gas? Is there going to be some effervescence? Or are they going to be staying in solution, right? That is important to figure out whether or not nitrate would be written back
You're
in
gonna
our
get a
ionic equation.
precipitate.
Repeat?
You're gonna get a precipitate.
Okay. You're gonna have a precipitate, right? And that precipitate would be our silver iodide, right?
Yes.
Okay. So that would be that, right? So what's happening to this? Would it be this here? Right? So is it gonna be in what state? The state I'm looking for. Right? We
Solid.
could use something like potassium iodide, right? Let's use potassium iodide and we're gonna get potassium nitrate out here. Let's get rid of that. Let's fill up this equation, right? So what I'm doing here is just using a simple metal that could be present here that would give us our iodine, right? So let's use silver iodide, right? This is silver iodide we dissolve to give us a solution of iodine ions, right? Iodide ions, so it should be fine. So can we get a ionic equation from this?
Yes, sir.
Yes, sir.
So what would be that ionic equation? The simplest net ionic equation. What would that be? So it would be our
Sir, I minus.
Okay, so you're asking me to write it. Okay, let me just I don't know. But go ahead. I minus. Go ahead.
Plus AG plus, oh sir, the state is aqueous.
Okay, the aqueous state. Aqueous state. Alright. And what will that
Here's
give
my
us?
82.
In this case, no.
So the silver iodide.
Remember, transition element ions, right? They have multiple states. And the silver iodide is yellow. This is our net ionic equation because our spectator ions will be our nitrate ions and our potassium ions because they're just out there like that. Alright, it's not gonna contribute anything. That's our net ionic equation there. Generally 2 marks. Right, state the result observed when concentrated ammonia solution is added to this yellow precipitate. When we add concentrated ammonia to silver iodide, what happens? Go ahead.
Sir, it's gonna dissolve.
Is it?
It won't dissolve.
Alright, so somebody says it won't dissolve.
Sir.
Go ahead.
Sir, sir, wouldn't we get sir, wouldn't the ammonia sir, is the silver iodide
Is the silver iodide? Go ahead. Come on, man. Well, when you think of the thing, right? I want you to just express what you're expressing.
But sir, isn't silver halide insoluble?
Yeah. So it won't.
So I think there wouldn't really be a reaction.
Oh, okay. Okay. First of all, there will be a reaction. Hold on. But what's happening is